Good evening, everyone. My name is Andrew Fracknoy. I'm the astronomy instructor here at Foothill College, and it's a pleasure to welcome everyone in the Smithwick Auditorium and everyone listening to us on the web to this very special lecture in the 12th annual Silicon Valley Astronomy Lecture Series. This series of public lectures, completely free to the public, is sponsored by NASA's Ames Research Center, the Foothill College Astronomy Program, the Astronomical Society of the Pacific, and the SETI Institute, and we're very grateful for their support. Tonight's speaker is Dr. Chris McKay of NASA Ames Research Center. Dr. McKay is a planetary scientist with NASA whose research focuses on the evolution of the solar system and the origin of life. He's best known for his work on Mars. He's been an investigator with several of the Mars projects, and he's actively involved in planning for future Mars missions, including the Mars Science Laboratory mission that's coming up, and also about thinking what might be needed for future human settlements on Mars. He has been a leader in polar research since 1980, traveling to the dry valleys of the Antarctic and more recently to the Siberian Arctic to conduct research in these Mars-like environments. He's on the board of directors of the Planetary Society and won their Thomas O. Paine Memorial Award for the advancement of human exploration of Mars in 1994. But the reason he's here tonight is because every once in a while he lets go of his passion for Mars and seeks understanding of other worlds, and he's been very involved in the mission to explore the realm of Saturn, and in particular, Saturn's giant moon, Titan. He was a co-investigator on the Huygens probe, which landed on this moon, Titan, the first human landing on a moon of a giant planet. And so we've asked him here tonight to tell us about Titan, an alien world with lakes, rivers, and, intriguingly enough, possibly life. Ladies and gentlemen, it's a real pleasure for me to present to you one of the real explorers of the solar system, Dr. Chris McKay.
I want to start by thanking Andy for inviting me to give this talk and Foothill College for sponsoring it. I've taken many classes here at Foothill, so it's always a pleasure to come here. As Andy mentioned, I'm at NASA Ames, just down the road, and my main interest is exploring the solar system and searching for life in the solar system. So I want to talk today about the prospects for understanding Titan, the large moon of Saturn, and the possibility that it might have life. And so we know it's got rivers, lakes, and the possibility that intrigues us is that it has life. The way I'm going to set this up is sort of a mystery. And of course, in a mystery story, you first start off learning what the mystery is, and then there's a lot of background information that you've got to trudge through before you get to the answer. So here is the mystery in the beginning. A few months ago, there was a paper that pointed out that there was a flux of hydrogen down through Titan's atmosphere into the ground. So I call it the case of the missing hydrogen on Titan. Where is that hydrogen going, and why am I so interested in it? Why did that report really spark an interest in those of us that were speculating on the possibility of life? So remember that. I'll come back to it. But of course, this is the point in the story where you now flash back and, well, why are you here? What's going on? And you learn about all the characters, and many, many pages go by before you get back to the mystery at hand. But it's the case of the missing hydrogen. So what are we doing here? Why are we out looking for life? I want to talk a little bit about why we search for life in the solar system, or why in particular are we searching for what I call a second genesis of life, because that's really what we're looking for. Why are we searching for a second genesis? Because we would then be able to compare the biochemistry of that life with our life. All life on Earth, we now know, shares a common biochemistry, a common genetics, and a common phylogenetic history, which is this tree of life. All organisms on this planet that we know of map onto a single tree of life. What we're interested in is finding another example. We have one example on Earth, finding another example, what I call Life 2.0. We're looking for a second example, because then instead of having a course called biochemistry, you could have a course called biochemistries. Think how many more textbooks that would involve, right? And the knowledge we'd have. Also, if we were to find out that right here in our solar system, life started twice, once on Earth, once on Titan, or once on Earth, once on Mars. If we found out that life started twice, then we would know that life is common in the universe. If it started twice right here. Just having one example, it's very hard to extrapolate. But having two would put us in a much, much firmer position in understanding that life is common. And I've added a little comment there, yay. It'd be great to know that there's life in the universe, know at the scientific level, and not in terms of rumors. And so we know what we're looking for. We're looking for life that is not like life on Earth, and we know what life on Earth is. It's organisms that map onto our tree of life, as it's called. It's not really a tree. Some people say it's a bush or a ring or a mesh connecting life forms, but the point is that all life forms on Earth have this shared biochemical history. What we're looking for, aliens. An alien is an organism that is not on this tree of life. That's the operational definition, and I show a picture of a possible alien taken from the NASA secret alien storage locker that people always ask me about, and of course there is one, and of course I would tell you about it and even show you a picture of aliens from the secret storage locker. It's funny, when I was a kid, an alien was an organism from another planet. So if you were from another planet, you were an alien, and if you were an alien, you were from another planet. But now we realize that that's an inadequate definition. An alien now is an organism that's different biochemically, even if it comes from another planet. So we might go to Mars and find life there, and it maps on our tree of life. It's not an alien, even though it comes from another planet. On the other hand, we might find something in the soil on Earth that we've never encountered before that is not on our tree of life, and then it is an alien. So we have the definition of alien has changed because of our understanding of biochemistry. And so when we search for another type of life, we're searching for a second genesis. Well, how might we get information about another type of life? There's really 3 programs directed towards searching for a second genesis, which I show here. One, we're going to make it in the laboratory. And that's getting closer and closer every day. In a sense, it's a race between these methods. We're going to make it in the laboratory, we're going to create synthetic life, and then we'll be able to compare it to our life. A hammer is not the tool they use to make synthetic life, but it was what I could conveniently find as an icon, so I put it in there. The other is to go find it on another world, and that's what I'm interested in. Go find it on the other world, and since the shuttle is its last flight coming up, I thought I'd put that icon there to commemorate the shuttle. Go search for it on the other worlds of our solar system. Those are the only worlds we can get to search for an example of life that we can study biochemically. We've discovered all sorts of planets around other worlds, and Kepler, that wonderful mission, is discovering them faster than they can be numbered. They've already got to numbers that exceed my ability to count. And that's wonderful, but we won't be able to go to those worlds and get an example of that life and map it onto our tree of life. The third approach, of course, is SETI. We listen for them to call. Well, I'm doing this middle one because I'm not very good in the lab, and I'm not very good at the telephone. My approach is go out and search for it. So that's what I'm going to talk about. How would we go search for life on another world? What would we look for? Where would we look? Well, ideally, we would take a tricorder and just cruise by and detect alien life with the tricorder. A wonderful device. You all recognize, of course, this scene from episode 26 of the original series, where with small adjustments of the tricorder, Spock not only detects alien life, but he detects silicon-based life. Wonderful tool. We should have one. Unfortunately, Unfortunately, science doesn't know how a tricorder works, doesn't know the principle on which a tricorder detects life forms. Even worse, science fiction doesn't know the principle by which a tricorder detects life forms. And I say that because if you go to Lawrence Krauss's wonderful book, The Physics of Star Trek, in which he explains warp drive, transporters, force fields, tricorders. No, not tricorders. He explains everything but tricorders. So even in the science fiction literature, we don't have an explanation. The other approach, common approach to searching for life, you can see the kind of literature I read, Calvin and Hobbes. We can't define it. We don't know what it is, but we'll know it when we see it. You can think of this as the Justice Potter Stewart approach to search for life. And that's okay if the organisms are big and they're chasing us or we're chasing them. But what we're likely to find, we know already, in our solar system is microscopic organisms, and the sample that we're likely to have is likely to be dead. So it's unlikely that we will be able to recognize microscopic life forms that are dead in either of these methods. So what do? The approach we're taking is to ask the question, well, what does life need? And go look in those kind of environments. So the approach is to say, what are the list of things that life needs? And the list is pretty short. It needs energy. On Earth, there's only two types of energy that life uses, sunlight and chemical energy. A particular type of chemical energy called redox chemical energy, shown, for example, by this reaction. So life needs energy, it needs carbon, it needs liquid water, and it needs a few other elements, nitrogen, phosphorus, and sulfur. The key requirement for life in terms of its distribution on Earth is liquid water. So liquid water becomes the operational constraint that we use when we think about life on other worlds. We say, what other worlds have liquid water? Those worlds usually have plenty of energy, plenty of carbon, and plenty of these other elements. So liquid water is the restrictive requirement for life, and that's why you often hear NASA's approach to search for life described as follow the water, search for the water. Not that life equals water, but that given all the things life needs, water is the hardest to find. So where are there worlds with water? But in fact, this slide is not worlds with water, it's worlds with liquids. Because you could argue that it's not water per se that life needs, but it needs some kind of liquid medium in which to do its chemistry. Life needs a liquid. Earth, that liquid is water. There's no other liquid that occurs naturally on the surface of the Earth. Mars, Europa, and Enceladus are all also water worlds. They're worlds that had water or have water under ice in the case of Europa and Enceladus. So there, we're searching for carbon-based life living in water, just like we see here. But it might be that on these worlds we find life, indeed, and they are related to us. They're not alien. Titan, the world of interest tonight, also has a liquid, and that liquid is not water. It's completely different. So if we find life on Titan, there's no chance at all that it is on our tree of life. Any life on Titan is sure to be alien because it's living in a fundamentally different liquid than life on Earth is. And that's why Titan is so fascinating to astrobiology, because even though it's so strange, its very strangeness ensures us that whatever we find there will be interesting if it's life at all. So that's why Titan is the focus. So let's go to Titan. So here is Titan as seen from space. It looks just like an organic fuzzball, like a tennis ball, because the atmosphere, Titan has a thick atmosphere, the atmosphere is rich with organics. Let me just do a quick comparison of Titan and Earth. Titan's got about the same size and gravity as the moon, so think of it as a moon-sized object, but with an Earth-like atmosphere. It's the only world with an atmosphere that's roughly equal to ours, in that its pressure is only 1.5 atmospheres. So if you were standing on the surface of Titan, it wouldn't feel that different than standing on the surface of Earth. It would be the same pressure you would experience under 15 feet of water. Swim to the bottom of a swimming pool, and that's the pressure sensation you would feel on the surface of Titan. It's also the only world with a nitrogen atmosphere like Earth's. So Earth and Titan both have nitrogen atmospheres. It also has rains and clouds and an active hydrological cycle, but instead of the liquid being water, the liquid is methane. It also has a strong greenhouse effect based on a different chemistry than the greenhouse effect on Earth. But the really big difference between Earth and Titan is on Earth, the temperature is plus 15 centigrade. On Titan, it's minus 180 centigrade. That's a big difference. Titan is really cold. It's like a mirror image of Earth, where the mirror is a freezing cold mirror. Everything that we see on Earth, all the processes that we see on Earth, we see cold counterparts on Titan. Now, of course, the folks on Titan are looking at Earth and saying, that world looks a lot like ours, only it's really, really hot, much too hot to support life. So that's one reason why Titan is so interesting, is this comparison to Earth. And part of this comparison is the organic chemistry. As I said, we see Titan's atmosphere. It's rich with organics. And we can simulate that in the laboratory. This, in fact, is a photograph of an experiment that was done in our lab at Ames. It was actually done by a high school student as part of what used to be called the Westinghouse Science Project. And what the student did is she hooked up a tank of nitrogen and methane flowing in, and then sparks in this chamber, and over time, the sparks created a reaction in the methane and nitrogen and created this brown organic material. And the spectral studies of this material show that it's the same as what we see on Titan from Earth and from spacecraft. So we can simulate the organic processes that are making this haze on Titan in the laboratory, and we can study them. And they don't have anything to do with biology. This is just sparks through a Titan-like atmosphere. And so in Titan's atmosphere, not surprising, there's all sorts of organic molecules. It's a real soup. It's the most organic-rich environment we know in the solar system. If you like organics, Titan has got lots of them. They may not be very tasty, but somewhere in the mix there's got to be things like chocolate and who knows what else. So Titan has got organics. And so searching for organic-based life, Titan is a place to go. So that's where we went. What we've learned about Titan has come from the fabulously successful Cassini mission and the Huygens probe. The Cassini orbiter was built by NASA. The Huygens probe through Titan was built by ESA. So I call this picture the ESA view of the European view of the Cassini-Huygens mission, seeing the probe up close, landing on Titan. And it's interesting, when we designed this mission many years ago, we were sure that Titan was covered by an ocean. So the probe was actually designed as a boat to float, and it even had sensors going through the bottom of the boat. We thought we were going to land like this on an ocean, or at least on the shore of a big, giant equatorial sea. The reason we thought that was because we saw methane in Titan's atmosphere, and we knew that with time, sunlight destroys that methane and turns it into ethane, and that would have happened in about 100 million years. So the only way Titan could still have methane after being around the sun for 4 billion years is if there was a huge supply of methane on the ground that was slowly being processed into ethane. So our concept when we built the probe was that we would land in an ocean of ethane and methane that would have been processed over time to produce that ethane from an initial inventory, ocean-deep inventory of methane. When we got there, to our surprise, what we found was essentially a desert world. The probe landed on the equator, not a drop to be seen. It looked dry. It looked like scenes in deserts on Earth. You go to the Mojave Desert and see scenes like this. It looks like rocks in the field. And the entire equatorial region, up to 50 degrees in both hemispheres, was dry. We didn't see any evidence of lakes or streams or ponds active at that time. But there were some curious results. One is that when the probe landed, the accelerometer trace indicated that the ground was soft. It landed with a splat not a splash or a thud. These are highly technical terms. A thud is what happens when you hit something that's really solid, and a splash is when you go into a water in the pool. And a splat is kind of something in between. Think of muddy ground. So this was one indication that the ground that we landed on, even though it looked dry, and here are the black and white image showing the scale. These rocks are about 15 centimeters in size. That it looks dry, but this is indicating that it's a little bit wet. And sure enough, one of the instruments on the probe detected vapor being released right after landing. So this is the landing point, splat, we land, and steam starts coming up from the parts of the probe that are sticking into the ground. The probe, of course, is much hotter than Titan because it's operating at electronics temperatures, and the Titan is minus 180 centigrade. So the probe is very hot, it heats up the ground, and we saw methane steam come out. So the ground was wet, which is a puzzle where we see what looks like a huge desert region in the equator of Titan, but the ground is wet. We did see clouds. These were storms seen by the Cassini orbiter as it was flying by Titan. These storms are at the polar regions. There's cloud activity in the poles, but the equator was without clouds and seems to be without clouds for most of Titan's year. Interestingly, at the landing site, we saw evidence of dried channels. We saw evidence of rivers that were now dry and what looked like coastlines, all now dry, arguing that maybe in the past, Titan may have had a global ocean or may have had large equatorial seas. But now, think of it as a desert world with mysteriously wet surfaces at the equator. Eventually, we discovered that there were lakes in the polar regions. This is Lake Ontario. It was named that because it's about the size of Lake Ontario. It's the only lake in the South Polar region. And in the North Polar region, many lakes were discovered. Here is different projections of that from Alex Hayes' PhD thesis. And here is Lake Michigan for comparison. So you can see these are Great Lakes. So in summary, Titan has lakes in the polar regions. You can see that this is extending down to about 70 degrees north only. So what we would call the Arctic and Antarctic regions on Titan have lakes, but in the equatorial regions and the mid-latitudes, it's a desert with slightly damp soil. So that's the world. It's got liquid. It's got liquid prevalent in lakes, but also in terms of wet soil. What does this mean? So one of the questions is, what is the possibility for life? And to understand that, I want to think about life on Earth viewed from space. On Earth, we have carbon-based life. It's made out of carbon. It lives in liquid water. And because it's carbon-based and because it lives in liquid water, it's everywhere on this planet. Because water is everywhere on this planet. So the life is widespread. Life on Earth is widespread. It's, in fact, very hard to find a place on Earth where there isn't life. I spent decades trying to do it. Find a place on Earth that's as lifeless as we can possibly find. And in fact, the most lifeless place we found is in the Atacama Desert in Chile, the driest place on Earth, where we find the least level of life. And still, it's teeming with life compared to what we expect to find on Mars or anywhere else. So even the most barren place on Earth is rich on life. And that's because carbon and water is prevalent on Earth. As a result of life being so prevalent, it has a global effect. It changes the world. Life has changed the world. And there's some obvious ways. The oxygen in our atmosphere is made by life. The fact that there's methane in the atmosphere at the same time as there's oxygen also is very odd and is due to life. And the CO2, that's my favorite example. CO2 has a very odd signature, which is due to life. Here is that signature of CO2 measured in Hawaii, and you can see CO2 in the atmosphere goes up and down, up and down, up and down, up and down. That is a signature of life. Well, on Mars, CO2 also goes up and down, but on Mars, the CO2 goes up in the summer and down in the winter. On Earth, it's going up in the winter and down in the summer. Exactly the opposite. And this, of course, is due to plants growing in the summer, eating the CO2, pulling it down, and then in winter, the plants die, the leaves die, the CO2 goes back in the environment. The CO2 goes up. This is a direct signature of life. Now, this increase with time could also be a signature of life, but that scientific observation has been trumped by ideology, so I don't want to discuss it tonight. But let's go back to Titan, where the science is still, science observations are still interpreted free of ideology. So back to Titan. Here, we have plenty of carbon, so we can postulate carbon-based life, but if that life is to be widespread, the liquid it's going to have to live in is liquid methane. The liquid on Titan that's widespread is liquid methane. So you can imagine, well, we should imagine life that's water-based on Titan, but if it is, we're not going to find it because there's no place on the surface of Titan where there's water. Why search for water-based life there? What we should search for is liquid methane-based life. Well, if there's carbon-based, liquid methane-based life on Titan, then it should be widespread. It should live in all these lakes. It should live in the wet ground. It should live everywhere on Titan, just the way water-based life lives everywhere on Earth. You have a planet or a world. It's not really a planet. It's a world. Planet is not a scientifically useful term, as we all know now, given the sorry fate of poor Pluto. But if there was life that could live in liquid methane, it could be widespread. And if it is widespread on Titan, it should change the world. That's the basic philosophy we're using to search for life on distant planets. We look at a planet around another star, we can't detect the life on that planet directly, but if life is widespread, it'll change the world just like it is on Earth. It'll create things like oxygen or methane or some global disequilibrium that we will recognize as a signature of life. On other planets that are Earth-like, we've picked oxygen as the key indicator. So when we see an Earth-like world around a sun-like star, we will look to see if it has oxygen, and if it does, that'll be very, very interesting. But Titan is not an Earth-like world. Life on Titan is probably not making oxygen. What is it making? It's living in liquid methane, and that's the key point here. So some of you may remember this famous cartoon, ammonia, ammonia, but we want to change that. Liquid methane, liquid methane. What could live on liquid methane, and what would it do? How would life forms living in liquid methane alter their environment the way life on Earth has altered our environment to create oxygen? What would be the global change effects that we could see from Earth or see from a spacecraft flying in Titan? So a couple years ago, together with a graduate student who was Heather Smith, who was then a graduate student, who's now since graduated and is working at the National Academies of Science, we did a study of what would organisms on Titan eat. Because if we go back to the things on Earth that life has changed, oxygen, CO2, methane, they're all things that organisms consume or release as part of their metabolism. They're either food or waste product. And in fact, one organism's waste product is another organism's food. So when we breathe in oxygen, we think, oh, this is all great fresh air. That's just the waste product of other organisms, algae and plants. So we looked at what would organisms on Titan eat and what would be their waste products. So what they eat, what an organism will eat, is something that it can get energy from. So here is the list that we came up with of the sorts of things that would be edible on Titan in terms of the kind of reactions, redox reactions, that life on Earth uses. The most edible thing, the tastiest thing on Titan, Titan chocolate, if you will, is acetylene. Acetylene plus hydrogen makes methane, produces a whopping 80 calories per mole. So what does this mean? It means that on Earth, what we do is we take in organic material, and as you can probably tell, preferably chocolate. We take in organic material and we take in oxygen, and we react that organic material with the oxygen to produce CO2, and that gives us energy. Okay, so we oxygenate organics. On Titan, there is no oxygen, but there's hydrogen in the atmosphere, and it turns out that organisms can make energy by hydrogenating organics, not oxygenating them. On Earth, we oxygenate organics because we live in an environment full of oxygen. On Titan, the strategy would be to hydrogenate the organics. So they react acetylene with hydrogen, and that gives them energy, and their waste product is methane. Other things that organisms could eat would be ethane, or even the solid haze would be edible. So if you're an organism on the surface of Titan, food is coming down from the sky, being produced by photochemistry, producing this ethane and hydrogen, which organisms can then eat. So it's easy living if you can live in liquid methane. It's easy living, and you can get plenty of energy that way. But if you say, well, what are the organisms consuming? They're consuming hydrogen, they're consuming acetylene, and they're consuming ethane. So in the paper we wrote, we pointed out, which is hard to see, but I'll read it to you, that if there was life on Titan and it was widespread, it would reveal its presence by anomalous depletion of acetylene, ethane, and hydrogen at the surface. So our prediction was the way life on Titan would change the world is not by making oxygen or seasonally varying CO2. It would change the world by eating all the acetylene, eating all the ethane, and most importantly, eating the hydrogen. That's what life on Titan would do. So this then takes us to the case of the missing hydrogen. So we wrote this paper. We submitted it the day the probe landed, just because we were late. We should have had it done a few years earlier, but we didn't. We submitted it actually the day before the probe landed. January 15th, 2005, the probe landed. We submitted the paper the day before, and we didn't really think much of it. It was just sort of idle astrobiology speculation about the possibility of life on Titan. And we went on to more serious things. Well, then a few years later, Darrell Strobel published this paper in which he concluded that the Cassini-Huygens measurements imply that something is eating hydrogen at the surface of Titan. Boy, this got our attention, right? I went through and found that old paper and said, wow, that's exactly what we predicted, right? Isn't that odd? And it is odd. And in fact, when I went back and looked at the three things we predicted, depletion of acetylene, depletion of ethane, and depletion of hydrogen, all of them were being shown to be true. So here's what we said. We said the results would implicate the presence of life by anomalous depletions of acetylene, ethane, and hydrogen. That's what we predicted would be gone. And acetylene is expected but not detected. Ethane is much more depleted than we originally thought it would be. These are not very important constraints because there's other ways we could lose those molecules. But the flux of hydrogen into the surface, there's no way we could explain that without biology. There's nothing eating hydrogen but organisms, which is why we thought that was a particularly strong indication of something odd and maybe biological, is the flux at the surface. And so what we expected then is that the Huygens probe, or any instrument, would detect a depletion in hydrogen. If there was no life, we expected the concentration of hydrogen to be constant in the lower atmosphere. If there was life, we expected it to drop off. Right? Now, we were thinking that the probe would detect this drop-off. Right? But there's confusing results. When we look at the results from the probe, which just came out a month and a half ago, the hydrogen concentration looks straight all the way down. You know, I would have been ecstatic if we saw a little drop here at the bottom. The hydrogen profile from the most recent analysis of the probe does not show any strong drop. But nonetheless, Darrell's model, go back to this, shows that there's still a flux into the surface. So in the case of the hydrogen depletion, there's one bit of evidence that argues for it, and one bit of evidence that seems to argue against it. If we confirm that there really is hydrogen lost into the surface, it's hard to explain that any other way but life. So let's go back to life. What would it be like to live on Titan? Would it be a difficult life? The challenges of life on Titan. First, as I said earlier, food is easy. It's falling from the sky. The organic haze being produced by the sunlight is the food that the organisms would consume. Carbon is easy. It's coming in those organic molecules. Nitrogen is easy. It's being incorporated into the organics by photochemistry. That's in contrast to Earth. On Earth, nitrogen is very hard. Biology has had to invent special tools to get nitrogen because the N2 in the atmosphere is so hard to break up. There's special nitrogen-fixing enzymes to do it. Hydrogen is also easy. What's hard on Titan is getting oxygen. You can't imagine organic-based life without oxygen. It's needed in many different molecules. It's not common on the surface of Titan. It's all tied up in rocks, otherwise known as water ice. So there's going to be special enzymes for these organisms needed to pull the water ice out of the oxygen out of water to use it in their biochemistry. The same way Earth life has had to invent special enzymes to pull the nitrogen out of the air to use it in its chemistry. On Earth, nitrogen is hard, oxygen is easy. On Titan, oxygen is hard, nitrogen is easy. So let's imagine we did go to Titan. And this is not a real picture of Titan. This is actually Lake Mead, modified by computer graphics to look like Titan. There's a film crew doing a special about Titan, and they sent me this image and said, does this look realistic? I was just amazed at how much it looked like what I would expect Titan to look like. But suppose we did go to Titan. We scooped up some stuff, and we wanted to know, is this gooey stuff from the bottom of the lake on Titan, is it Titan life? How would we tell? It's going to be alien. It's not going to be life like we know it. But that's the whole point. We want to find life like we don't know it. Well, how would we detect it? What would be in this liquid? We don't know yet. We're just starting experiments to see what kind of organics could dissolve in a liquid like this. Would this soup be a thick soup or a thin soup? Well, we already know that it's going to be a pretty thin soup, but just how thin it is, we don't really know yet. We're just doing those experiments now. But if we imagine that there is life on the shore of these lakes, how would we recognize it? What would we look for? So I want to make a suggestion that there is a way to tell the difference between organics that are produced in the atmosphere, like in our Titan simulations, that are just abiological organics, and organics that are produced by a biological system. Biology is a lot more picky than chemistry, shown by this schematic plot. So I'm plotting concentration versus type of molecule. A non-biological distribution has got all sorts of types of molecules more or less at the same amount. Everything is in there. Whereas biology picks certain molecules and uses only them. For example, biology uses L amino acids, left-handed amino acids, and not right-handed amino acids. Hooray for lefties. That's the only kind of amino acid that biology uses, whereas if we make amino acids in a chemical experiment, we make both right and left-handed. So biology chooses, chemistry doesn't. And we can see that by looking at the distribution of organics. Now suppose we go to Titan and find some organic material, and we find that it also has an unusual distribution, but the distribution is different from the distribution of Earth life. That would be evidence that that organic material was produced biologically. And it goes back to this example here about life choosing the L, the left-handed amino acids, and not the right-handed amino acids. Biology chooses, chemistry doesn't. That is, I think, the most fundamental principle that we can generalize to searching for life that's not like us. It wouldn't do us any good to search for DNA. We know how to search for DNA, but if there's life on Titan, it's certainly not using DNA. It's not using the same molecules that life on Earth uses. So we need a more general principle. And that more general principle is life chooses, but chemistry doesn't. I want to end by going beyond our solar system. There's a real excitement now in the planetary community, the discovery of planets around other stars. Our goal has been to search for Earth-like planets. That's cool. I'm all for Earth-like planets. But we ought to also search for Titan-like planets around other stars. Because Titan is so cold, it doesn't have to be so close to the star to be habitable. So we talk about liquid water habitable zones. And unfortunately, the most common type of star, an M star, red star, all those of you who remember Superman comics know that he came from a red star, of course, because there are more red stars than any other type of stars. But life in a water-like world around an M star has to be uncomfortably close to the star, so close that it's probably tidally locked. But if you're living in a liquid methane world, a Titan-like world, then you're much further from the M star. So a Titan-like world could be habitable around an M star at a much further distance, and it wouldn't be tidally locked. And Jonathan Lunine, a scientist involved in studies of Titan, has suggested that there may be much more Titan-like worlds in our galaxy than Earth-like worlds, because they could exist around these small, dim, very numerous stars. And when we look at Titan, we think, boy, it's going to be hard to live there. But if we imagine the view from Titan, I have this slide here that I call Rare Titan. And it's kind of a spoof on the book Rare Earth, which some of you may be aware of, in which the authors, my good friends Don Brownlee and Peter Ward, brilliant guys, and I like them, but I don't like the conclusions of their book. They said, well, Earth is really unusual and really special, and there's not going to be very many places like Earth. And I think, well, imagine there was a Don Brownlee and a Peter Ward of microscopic proportions living on Titan, writing a little book called Rare Titan, in which they point out that, okay, we've got this other world in which there's water, but it can't really have life. It's another world with liquid, but that liquid water is extremely corrosive. It dissolves organics, it even dissolves inorganics. Its solution concentrations are so high as to be toxic. The high temperatures would require organisms on that world to eat several times a day. Right? How could that possibly be? And the solid phase would float over the liquid phase, creating a temperature instability that could cause runaway glaciations. And on their list would go, proving that there couldn't be life on that water world and proving the suitability of the Titan environment and the intelligence of the design of the liquid methane environment suitable for life. So it makes the point that maybe as we learn more about life, we'll realize that it's perspective on, we'll get a different perspective. And this is the slide that tells me it's the end of the talk and time for questions. Thank you. Start right here.
Yes, regarding flux of hydrogen down, as I understand it, that means that hydrogen is moving down through the atmosphere toward the surface of Titan. So wouldn't that also mean that there has to be hydrogen going back up again?
No, that's exactly why it's a mystery, is that there's a flux of hydrogen into the ground and that's it. According to Darrell Strobel's study, there is a sink, a loss of hydrogen. So it's flowing into the ground and then something is consuming it. And now that hydrogen may be reappearing as methane, CH4, coming out, but it's being changed. It's not coming out as hydrogen. And that's why it's a mystery. Something is consuming the hydrogen, if he's right, if Darrell is right. And what could be consuming the hydrogen? Well, my favorite answer is biology. There's no chemical process that we know of that would operate at these temperatures that would consume hydrogen. So it's very curious. Question over here.
Thank you, Dr. McKay. it has become apparent that for manned missions in space for longer than 90 days, we need substantially more shielding against cosmic ray particles than is economical to launch. And one solution that has been proposed is robots welding or fastening spherical asteroid components into a hull of sorts to shield. And in order for robots to do that, they would need a replenishable propellant. The nuclear reactors could keep going for some time, but the propellant would need to be replenished. So the two alternatives are nitrogen from Titan's atmosphere in an ion engine, or the ice and dry ice from comets and main sequence comets in the asteroid belt. Which do you think would be the more economical, given the gravity well of Saturn and such, which do you think would be the more economical source of propellants?
Yeah, well, that's a fundamental problem. As long as you're using rockets, you have to exhaust something out the back end. And if you don't bring it from Earth, you've got to find it in space. I don't think either of those is going to prove, the two methods you suggest were using nitrogen on Titan or volatiles from comets as the propellant in some sort of propulsion system. I predict that neither of those will prove to be economical. We need to invent a different type of space transportation than rockets. Now, my personal favorite, of course, is warp drive, but I'm willing to accept something intermediate. But I don't think, so I think it's a tough problem, and I think the engineers ought to get working on it. So if there's any engineers in the audience, don't sit here, go get working on it. The rockets are just too limiting to get through the solar system. The solar system is too big for rockets. We need a new technology, and I don't know what that is. Question here?
Since this talk was really more about life than Titan, I think, a few days ago a paper surfaced by Richard Harris in this so-called Journal of Cosmology about ancient alien fossils in meteorites. Is this junk or is this science?
Well, that's a very timely question. There was a big blurb in the internet over the weekend because of a paper in a sketchy online journal called the Journal of Cosmology, in which Richard Hoover, who's a friend of mine, reported seeing structures that he identified as biological in origin. Not just biological in origin, but a particular type of organism, cyanobacteria, and what's more, identified heterocysts of cyanobacteria. Well, cyanobacteria are photosynthetic. They live in water with sunlight, and heterocysts are structures that cyanobacteria make to protect their nitrogen-fixing enzymes from oxygen. So the presence of heterocysts of cyanobacteria says that he is saying that these meteorites came from an environment with water, sunlight, and oxygen. That is radical. The alternative is that he's just seeing some bizarre shape that's got nothing to do with biology. So you either have to accept that there's strange little shapes in meteorites, or that meteorites come from a world that's strangely Earth-like, out of context of our understanding of meteorites. Now, if I had to choose between those two, I would choose it's just a shape. And at that scale, shapes don't tell you anything. You think about it, these shapes are micron in size. You think of a meteorite that's, say, 10 centimeters. There's something like 100 billion square microns in the cross-section of that. So you're going to probably find something that looks like, you know, anything you want. You know, take a picture of one of your friends and search through it, and you'll find a picture of your friend in the meteorite. Will you then conclude that the meteorite came from a world that was populated by organisms that look like your friend? I don't know. You just conclude that, well, isn't that curious that this shape had that odd proportions? Now, I don't think it's contamination. I don't think it's sloppy technique. Richard Hoover's actually very good at microscopy. But I just think that you can't unequivocally deduce biology from shape when you're looking at those kind of tiny shapes. You'll see every type, every structure you can imagine. Question over here.
Regarding signatures of life in the chemistry of Titan, have any researchers been modeling or simulating evolutionary pathways of organics into more and more complex molecules over, you know, simulated many large intervals of time?
Yeah, that's a very important question, and I carefully avoided talking about how life got started on Titan. I only talked about the energetics and what the effect would be, and I didn't say how could you get life started in such a cold, organic, poor mix as we see as we expect in the lakes there. And part of the reason I avoided it is because we don't even know how life got started here. And here we've got lots of scientists working on biology full-time, or at least part-time. So we don't understand how life got started here, so we shouldn't expect to understand how it got started there. But it is probably the most difficult part of postulating life on Titan is postulating how it could get started, how the kind of self-organizing of organic molecules that we think leads to life could happen in a organic mixture at such low temperatures. We're thinking. I wouldn't say we're working on that because that would be a slight conceit in terms of the level of our understanding and effort, but I'd say we are thinking about working on that. And thinking about what kind of experiments would we do to try to simulate organic prebiotic chemistry in a liquid methane-like solution. And the answer is we don't have any good ideas yet, but we're still thinking. That's what we get paid to do, you know. Question here?
Can you hear? Oh, yeah. You suggested that probably the only way to get oxygen connected up with the CHN would be some living process. Are there specific compounds that could be detected spectrographically from satellites or some probe? In other words, would future missions be designed to look for something that had oxygen combined with it?
That's a good point. That's a very good point. And that is, if there's no life on Titan, the oxygen content of the organics on the surface should be very low. If there is life on Titan, the oxygen content of the organics on the surface will be higher because those organisms will be scavenging oxygen and sticking it into their biological molecules. And that, I don't know of any way to detect that from orbit or from Earth, but we could detect it when we land. And it's part of the whole idea that if we can land and scoop up some organics, if there's life there, we'll see it by the signature in the organics. Because it will look different than the stuff produced non-biologically. And that will be a very good example of the kind of difference. It will be enriched in oxygen. The same way that on Earth, organic material is enriched in nitrogen compared to what you'd expect from non-biological processes on Earth. Earth life specifically collects nitrogen and phosphorus, and so biological or material of biological origin on Earth is enriched in those elements, nitrogen and phosphorus. And nitrogen in particular, people have suggested that could be a way to detect life on Mars, is look for nitrogen, follow the nitrogen. On Titan, it would be follow the oxygen. Good point. Question here.
Again, piggyback on that a little bit, talking about signatures of organics. Is that something you can start doing now? Is that something you've already started doing? And what does it take? Does it take maybe a probe to the planet, to the moon? Does it take a satellite orbiting, or does it, a Hubble image with RF spectrum?
I think to analyze the organics, we've got to land and scoop up the organics. We don't know of any way to make the analysis at the level of precision needed remotely. We've got to scoop it up and then stick it in an instrument like a GCMS. Stick the organics in there and then look at what we see. We've flown those kind of instruments. We've flown them on Viking. We've flown them on the Huygens probe. We've flown them on the mission that's going to Mars in November. The Mars Science Laboratory is on its way to Mars. It launches in November. It will have a state-of-the-art GCMS with both liquid and pyrolysis extraction. That instrument would be perfect to send to Titan. The problem is getting it there. It's a long way away. And landing it safely and then getting the soil up from the ground and into the instrument. But we have the instrument, we just don't have the spacecraft to get there. Question here?
One thing that fascinates me about what you've been talking about is the implications of life at such low temperatures. And you've already indicated that if life at such low temperatures were to look at us, they would think, my God, no one, oh my God, eating 3 times a day at such a rapid pace, how can they live with that?
Right.
Sometimes I wonder myself.
Yeah.
But when we look around the Earth, we've recently, the last 10 years, 20 years, discovered life in places we didn't expect it, whether it's in deep ocean vents and very high temperatures, and the acidic environments, or what we would think of as poison environments. But if I'm not mistaken, I recall there was life discovered a mile or 2 underground in rocks with incredibly slow metabolism in that kind of environment where cell division might take 1,000 years.
Right.
And I'm just curious, with my laying those possibilities, those things out, what you have to say about what would the implications be of life taking place at low temperatures and with such, I presume, a low rate of metabolism?
Right. You're certainly correct that on Earth we find organisms living very, very slowly, living at low temperatures, metabolizing at a very slow rate, or living in environments where they spend most of their time frozen or starved, and hence are in a stasis, and so their life cycle is stretched out over literally geological time scale. So we even see that on Earth. So on Titan, that could be taken to an extreme. It could well be that the cycle time of an organism, the metabolic lifetime, could be thousands and tens of thousands of years. But if you think, what's the hurry? If everybody is living at that same time scale, if the organisms you're chasing and the ones that are chasing you are also moving at 1,000-year paces, you know, everybody's going at the same pace, who's to say that that isn't fine? So there's no intrinsic time scale that life must keep up with. So I don't see any fundamental reason why it couldn't be true. The life on Earth at very low temperatures and very long time scales is in a way a model. But I think if we do find life on Titan, it'll be even slower still. It will give a whole new meaning of life in the slow lane.
Okay. On Earth, our water-loving life makes use of the fact that the water molecule has a dipole moment.
Right.
Whereas on the methane and ethane has no dipole moment. I'm wondering if there's anything at all soluble in methane, ethane that does have it. Like, is ammonia at all soluble, or is there some organic molecule with a dipole moment that could be in there? Or you really have life operating in a different kind of chemistry?
Have you been listening in on our lab meetings? Because that's exactly this today at, what was it, 1 o'clock or 2 o'clock? One of those o'clocks. We were talking exactly about that. Okay, methane isn't working very well, non-polar solvents aren't working well, maybe a little bit of a polar solvent added in would spice up the mix and allow for enhanced solubility. It's like, you know, just putting a little bit of alcohol in the water changes
I wasn't eavesdropping.
That's all right. If you have any good ideas, email them to me. We need them, really. But it is an interesting possibility because we have theories which suggest that there is ammonia on Titan. It's going to be mostly frozen and solid. But the literature suggests that there should be some small solubility of ammonia in the liquid methane. And that could really change its solubility chemistry. But the experiments are very hard to do. I can't do them, and the highly qualified technicians in the lab that are working on it can, but it's still very hard. We're working at very cold temperatures, and the things you normally like to do, like sonicate a sample, shake it up, are very difficult to do if the sample's at minus 200 centigrade. So practical problems are preventing us, but the line of thought, I think, is brilliant, if I do say so myself, because we've been thinking the same thing, which goes to show that great minds are all in the same rut. Question here?
So are there any more return trips to Titan planned, say, in the lifetime of any of the young people here?
Are there any more trips to Titan planned in the lifetime of anybody here? Well, trips to Titan take a long time. When I started working on Titan, on the mission, the Huygens mission, to when the data arrived was just 2 months short of 20 years. So from start to data was 20 years. So if we start again now, it'll be another 20 years. And in 20 years, we'll all be 20 years older than we are now. That's the way it works out. So, and we're not starting a Titan mission right now. The decadal survey just came out last week, or yesterday, Monday, establishing the priorities for planetary science. And Titan mission was about fourth. So first was Mars sample return, then was Europa, pretty interesting world, half as far away as Titan though. Mars is really close. We can get there in just 6 months. We can do a Mars mission from start to finish in about 4 years. Titan, it's more like 20 years, just because it's so far away. So Titan is a few missions down in the queue. So maybe we'll start one in another 15 years, and then it's another 20 years to get there. So these predictions about life on Titan won't be disproved anytime soon. So I'm free to continue giving talks, speculating about life on Titan. Who knows? Now, on the other hand, there's a bunch of clever engineers trying to come up with simple missions to Titan that might be able to sneak in, like a mission that just lands on a lake and measures what's in the lake, or an airplane mission that flies through the clouds. Those kind of missions are less expensive and could possibly get in as a faster, nearer-term mission. That might be only 15 or 20 years from the new start, which could be in a couple years. So maybe. So if you want to see a Titan mission, plan on living for quite some time. Don't smoke, exercise regularly, eat right, get plenty of sleep, and just think liquid methane. I guess next question over here.
Towards the end of last year, there was some interesting publications about work at Mono Lake by, I think it was Wolf Smith and her team, looking at arsenic as a life process in some potential bacteria that they had found. Does that count as being off the tree, and did it inform your work in any way?
Yeah, that's a good question, and it's timely. What that work was, there was a paper in Science that reported an organism identified from Mono Lake, a Californian, that was able to utilize or survive, I think technically, survive very, very high concentrations of arsenic. Arsenic is poison. The reason it's poison is because it's a lot like phosphorus. Phosphorus is an essential element. Arsenic sneaks in and pretends like it's phosphorus and gums up the works because it's right below phosphorus in the periodic table. So the idea of searching for phosphorus-based life actually came out of a meeting at Arizona State a few years ago where we were trying to come up with ideas. What could we look for on Earth to find organisms not on our tree of life? And one idea was, well, if we can find an organism that doesn't use phosphorus, that uses arsenic instead, that's pretty weird, and maybe that won't be on our tree of life. Well, it's kind of a success, but not. They found an organism that can survive extremely high concentrations of arsenic, maybe even uses the arsenic as a replacement for phosphorus, although that's not really anchored in the results, and it's still controversial. But it is not an alien organism. It is a normal organism that normally likes to eat phosphorus, but it will use arsenic or tolerate arsenic if the phosphorus is very low. But it definitely is on our tree of life, maps onto the bacterial kingdom, and it's got the same ribosomes and triplet code and all the things we know and love about life on Earth. So it's one of us, just a strange one of us. But this is California. We accept all kinds. They wouldn't allow it in New Jersey or New York or the East Coast or any of those red states, but here, we'll take it. Right? Hooray for diversity in life. Question here.
So if life was found on Titan or a planet like Titan, would that change the Drake's equation in some way?
Yeah, that's a really good question. The Drake equation, in fact, most thinking about life beyond the Earth and its distribution in the universe is based on our water life paradigm. We say, how many Earth-like life worlds could there be? What fraction of Earth-like worlds could have life? What fraction of those Earth-like worlds with life would have intelligence? That's the basis of the Drake equation, is those estimations. But it starts with an assumption that the life form is going to be like us, living in water. If we expand that to include liquid methane, Jonathan Lenin's point is there could be way more methane, liquid methane worlds than water worlds. And the reason is the universe is a cold place. It's hard to make it warm enough for water. It's a lot easier to make it warm enough for liquid methane. So there's, in a general sense, a lot more phase space available for cold planets than for hot planets. And so, yeah, it would affect our estimation. Now, would that methane life have the possibility to develop intelligence? And you didn't ask that question, but I'm asking it for you. That's more problematic. It may be that the answer to that would be no, that it's going to only be microbial. But let me think about that. Maybe we could come up with some reason why methane-based life on Titan could develop multicellularity and hence intelligence. On Earth, multicellularity is rooted in oxygen metabolism. We don't get multicellular life until we got oxygen. And all complex large life forms use oxygen. Or they breathe oxygen like humans do. And so many people conclude that an oxygen-rich atmosphere is a prerequisite for multicellularity and a prerequisite for intelligence. But they haven't really thought a lot about liquid methane life. So maybe there's a way around that problem. That's a good thought. Question here.
It does seem reasonable that regardless of the biochemistry, you would expect life forms to be organized into cells. Given that, you focused mostly on biochemistry tonight, but are there efforts underway to deploy microscopes, remotely operated microscopes or cytometers or other kinds of instruments that could look for those small organized structures?
Yeah, that's a good point, and it certainly would be true that if there was life on Titan, it would compartmentalize itself. And one of the questions we're asking is what kind of molecules would it use to compartmentalize itself? Life on Earth uses lipids. Lipids work because they have a hydrophilic and a hydrophobic end. So lipids work because they act against and with water. On Titan, you would need a different organizing principle to create compartmentalization. Maybe someday you could try to search for that with a microscope, but that's not what I would send as a first instrument. I would send something more general like a GCMS and just look for unusual patterns like high oxygen, as we talked about earlier, or chiral asymmetry, all of certain left-handed or right-handed, or some other signature in the organics that's a little more general and easier to spot. Whereas microscopes, it goes back to the question about the meteorites. If you look at something on a very, very small scale, you see all sorts of strange shapes. And they're no longer, the shape no longer becomes characteristic of biology. We're used to thinking of dinosaur fossils where just the shape of the fossil tells us that it was alive. But those are things that are large. When you get to things that are a micron big, there's so many different shapes that shape is no longer a sign of function or sign of origin. And so I would be very leery to argue for a microscope as a way to search for life on an early mission. Once we detected life and we know it's there, say with some biochemical approach, then you might want to send a microscope to have a look at it, because then you've got more of a context to put it in. And that same logic, I think, applies to Mars. A microscope is powerful, but it's only powerful when you know what you're looking at. And that's the problem with the meteorite searches.
Let's say that only the people standing now.
Okay. So 3 more questions on either side, so that's good. Question here.
You mentioned the length of time to search for life, and of course, Europa and Enceladus, water-based, would be somewhat difficult. However, I'm wondering, instead of trying to land on them and drill or melt down through several kilometers of ice, what would you think about sending a spacecraft to the Lagrange points around Europa and Enceladus? Because through either the eruptions on Enceladus or impacts on Europa and also on Enceladus, there should be a lot of stuff hanging out there.
Yeah.
And wouldn't that be a faster, cheaper, and perhaps better way of doing it? Flybys through the fizz coming off of Enceladus gives you a very brief snapshot, whereas shouldn't there be a lot of stuff that's been accumulated at the Lagrange points?
Yeah, it's a good approach. There's two parts to the approach. One is catch the stuff that's flying off, and two, catch it where it's accumulating. Now, in the case of Enceladus, it's definitely flying off. We can fly through the plume. It's also accumulating, but not at the Lagrange points. It's accumulating in the E-ring. The entire E-ring of Saturn is Titan is from Enceladus. So when we were thinking of a sample return mission, we're thinking of flying through the plume of Enceladus several times, and then going through the E-ring and picking up some more stuff, sort of catching the stuff that's been caught by Saturn, because the stuff that leaves Enceladus is still caught by Saturn. Europa is a much harder case because we don't know for a fact that anything is jetting off. There's one hint that there are eruptions from Europa, and that was during the Galileo mission. One of the flybys saw a very high increase in plasma density, electron density, factor of 10 over all the others. And one interpretation of that is some sort of plume or eruption. So I've argued that if we do a Europa orbiter, we ought to be watching for eruptions and just watch an orbit and catch it as it comes out. And if it's coming from the ocean, it should contain interesting things in it, like argon dissolved in the water, that we wouldn't see if it was just coming off the ice. I'm not sure. I haven't thought about the possibility that that stuff would be caught at a Lagrange point or an orbit around Jupiter. I'd be more interested in catching it fresh, which we could do with an orbiter. So I'd argue that the way to do that is watch in an orbiter, and if you see an increase in density, there's something happening, capture that. And the Galileo data suggests that that's a plausible scenario. Question here?
If I recall some of your slides correctly, the liquid methane lakes are concentrated along one of the polar regions.
Right.
Presumably, the solubility and diffusion rates of this molecular hydrogen within this kind of slushy solid surface in the equatorial regions and in the actual liquid methane lake or lakes is very different, and presumably the magnitude of life would vary across the planet. The question is there any atmospheric modeling or any atmospheric tracer that might favor non-uniform distribution of life that one could pick up remotely, or is there just too much atmospheric turbulence that smears everything out?
No, that's a good question, and it's a good suggestion, and it may even be happening. The question is there something we can see in the atmosphere that would vary with latitude that indicate that life is rich in the lakes and not so rich in the desert? And in fact, a couple years ago, a friend of mine in Paris, Regis Courtin, sent me an email showing that his analysis of the Cassini data indicating variations in the hydrogen concentration with latitude. Because hydrogen is the thing that the bugs are going to change, that nothing else can change as easily. And so I wrote him back and said, well, this is obviously signs of life. Not really, but that's the answer, is if the hydrogen really is, if the organisms are really eating hydrogen, and you have more organisms at the pole and less at the equator, then you're going to get a latitudinal variation in hydrogen as well as its consumption going down. So hydrogen is the molecule to track, and that we can detect actually at some level from the Cassini orbiter. And that orbiter, of course, is still going around Saturn. We're still getting more data from Titan. The mission continues, more data comes in, and the analysis of the hydrogen is still being done. So the story may still be written in terms of what's happening with the hydrogen.
You didn't mention anything about the
possibility of a hot core on the planet? Is that, could that contribute to increase the chance of life by having, localized hot spots to accelerate processing?
Yeah, we think that Titan probably has some activity subsurface, and we base that on the fact that since there was no ocean, how is it getting methane? We speculate that it must be coming out through volcanoes, so there must be some sort of source. We haven't seen any. We have no evidence of volcanoes, but we believe that they're there just from this theoretical argument. So we believe that there must be a subsurface ocean and heating and a core. So we have theoretical evidence, if you will, if that isn't a contradiction in terms. We have theoretical indications that there is active interior. Whether that's going to be important biologically, I don't see a connection. The surface is so rich in energy and organic sources coming down from the atmosphere that organisms would not need to use any geothermal sources for geothermal energy. There might be some that do, just like on Earth, most life depends on sunlight, but there are organisms nonetheless that depend on geothermal processes. That may be also the case on Titan. We have no way of knowing, though. Question here?
Excuse me, but if there is life evenly spread up in a vertical axis in the atmosphere, which would explain the evenly spread hydrogen, could volcanoes spread oxygen if needed to the life, and to get frozen ice? Could it use some sort of super powerful antifreeze, which could be used on modern cars in Wisconsin, all those places?
Yeah, there's two questions there. One is, could there be life in the atmosphere itself? It's a good question, and we haven't thought of it before. There's a lot of organic material in the atmosphere, and there's a lot of energy sources in the atmosphere, and there's even liquid methane in the atmosphere, just like there's liquid water in clouds on Earth. And people find life in clouds on Earth, so maybe there could be life in clouds on methane. So it's something, it's an interesting idea, and it's worth thinking about. Could the life be in the atmosphere as well? In terms of how would that life get oxygen if they're not decomposing rocks, we know that there's a very small flux of oxygen coming in terms of meteorites burning up in the upper atmosphere, very low levels, producing a CO level, for example, of about a part per million. The organisms could be very efficient at scavenging that if they lived in the atmosphere. In terms of the antifreeze question, now that's a different question. On Earth, we look at Titan, we see it's very cold, we need antifreeze. But to an organism that grew up in minus 190 Kelvin, they wouldn't need antifreeze. They would say, this is just fine, right? So they probably have not invented antifreeze. They've just learned to live in that temperature that is the temperature of their environment. To make water liquid at that low temperature, you could put an antifreeze in it, like ammonia, and then you could have water at very, very low temperatures. But we don't see any evidence of that on the surface of Titan. The liquids we see are liquid methane, not ammonia, water, cold ammonia water mixtures. Question here?
As you know, life is a very simple cells are very intricate mechanisms which require a vast amount of information stored in the genetic material. What do you postulate as the molecule capable of storing this kind of information in the very simple hydrocarbon chemistry of Titan?
Right, that's a good question. I don't think you can with just simple hydrocarbons, which is why you need oxygen and nitrogen. You need the full complexity of all four molecules, C, H, N, and O, to make the kind of complexity required for information storage and translation and expression, all those things. So I think you get the C for free, you get the H for free, and you get the N for free on Titan. But you have to work to get the O. So I think life will have to have solved that problem, because I think from an information theory point of view, you're going to need all four molecules. Now, you say, okay, well, what molecule does it actually use? Well, I have no idea. But at a broad sort of theoretical level, I think you're going to need the degrees of freedom that come with having more than just hydrocarbons. You're going to need nitrogen, you're going to even need more than that, you're going to need oxygen. So I can make a general argument that you need the complexity that comes from that diversity of molecules, but I can't answer you in specific what is the equivalent of DNA. Question here?
Hey, so on Earth, certain organisms take in oxygen and turn that into CO2, and then other organisms take that CO2 and turn it back into oxygen, sustaining themselves. If on Titan, organisms are taking in CO2 and spitting out methane, in order for that to be sustained, doesn't that mean that other organisms have to take in that methane and turn it back into hydrogen?
Yeah, it's a good point. On Titan, the acetylene and hydrogen is made by the sun.
Okay.
So the equivalent of what plants do, which is to take sunlight and make food, on Titan, that's occurring without plants, without life, in the atmosphere, and we know that's happening. So food is being made in the atmosphere and raining onto the ground. So all we need is someone who's willing to eat it, right? On Earth, there is no food being made in the atmosphere. One theory for the origin of life is that's how life started, with free food. But now the atmosphere is oxygen rich and there's nothing being made in the atmosphere, so plants are making the food and then heterotrophs are eating the plants. So that's the cycle you referred to. On Titan, the phototrophs don't exist, it's just being made in the atmosphere. So the simple cycle we imagine is sunlight makes acetylene and hydrogen. By the photodissociation of methane, that's food, it comes to the surface, organisms eat it, making methane, which goes back up and then gets hit by sunlight. So it's a free lunch. It's a very cold free lunch, but it's a free lunch.
Thank you. That's actually really cool.
All right, the last question is here, right? Yep.
Since Titan has a gravity, would that mean that its atmosphere could be contained and have an orbit?
Well, Titan has a gravity about the same as the Moon's. The Moon, as you know, doesn't have an atmosphere. None of the other objects in our solar system that are the size of the Moon have an atmosphere. But Titan, which is also roughly the size of the Moon, does have an atmosphere, and it's even thicker than Earth's atmosphere. That is a mystery. Solve it and let me know what the answer is. We don't know. There's one theory by a colleague whose office is just down the hall from mine, so I must believe this theory, that it's got to do with the effects of Jupiter versus Saturn, and on Saturn, the impacts were so strong that they destroyed the atmosphere, or Jupiter, but on Saturn, they were weaker. But the real answer is we don't know. So it is a little bit of a puzzle why such a small moon has an atmosphere and why that atmosphere isn't lost to orbit around Saturn, the way the stuff coming off Enceladus is lost to orbit around Saturn. So it's a puzzle, but it's a fact that it does have an atmosphere and a very thick one. And to me, that raises the possibility that small worlds around other stars could also have an atmosphere. So, yeah, just because we can't explain it doesn't mean it doesn't exist.
Thank you.
Thanks.